Hi everybody, these are just some summary notes for year 12 physics on light. So we see objects when light from the object enters our eye, and there are two types of images that are possible. So if we see something where the object is not actually there in that particular position, we say we see an image. Now, the real image is formed when light rays actually cross each other. So intersection means cross each other. And a real image can be obtained or formed on a screen. A virtual image is formed by the apparent intersection of rays, and this is done by producing the rays of light backwards. And we have to look into the mirror or the lens in order to see a virtual image. Okay, so the terms used with curved mirrors. So we're only looking at concave and convex mirror. So a convex mirror is the one that bulges outwards. So the shaded thing is the back of the mirror, and the unshaded is the front of the mirror. And so that's your convex mirror. Here's your concave mirror. So caving in. So that's how you remember. Okay, so you've got the principal axis, which is this imaginary line that goes through the pole, the focal point, and the center of curvature. And the pole of the mirror is on the surface of the mirror at the center of the mirror. The center of curvature is the center of the sphere of which the mirror forms a part, and halfway through is your focal point. It's also the point where parallel rays will either appear to meet or actually meet when they fall on the mirror and they get reflected from the mirror. So they all go through the focal point. Okay. And when rays meet, you say they converge, and when they go away, you say diverge. So a convex mirror is also called a diverging mirror because it spreads out the rays of light. And a concave mirror is also referred to as a converging mirror. Converge means to come together. Now, ray diagrams. In a plane mirror, you always, whichever mirror it is, you always have the angle of incidence equal to the angle of reflection. So this is what happens in a plane mirror. Now, in a concave mirror, I've just drawn, there are many ways of drawing this, but you only need to choose two rays, and you just need to be careful when you're drawing these ray diagrams. The distance from the mirror to F is exactly the same as the distance from F to C, and I've just used two of those rules. Any ray parallel to the principal axis will go through the focal point, and then I've just drawn another one. This is a ray that goes back and forth along the same straight line. Anything going through the center of curvature, it's like going along the normal. So you only need to draw one line, and where the two lines cross or meet is your image. Now in this one, they actually meet, so you get your real image. And you often have to describe the image, the nature of the image. So it's real, inverted, enlarged, and where is it? Position is beyond C. Okay, that means it's quite far away from there. And in a convex mirror, you always get an upright virtual diminished image. And so this is how you draw that. So any ray parallel to the principal axis appears to come from the focal point. And any ray going through the center of curvature will go along the same straight line. And where the two rays appear to meet, you get this tiny little image there. Okay, and the mirror formula, there are two of them. So what we do when solving problems is we take real is positive, virtual is negative. You've got to put the negative sign. So the focal length of a convex mirror is always negative, so your F is negative. And if the image is virtual, then that will be negative as well. All the object distance will always be positive because that's always in front of the mirror. Okay, so M is equal to HI by HO equals DI by DO. M is magnification, height of image, height of object, distance of image from the mirror, distance of object from the mirror, and then you've got 1 over DI plus 1 over DO equals 1 over F. Okay, moving on. So refraction of light. So this is when light travels through from one medium to another. What happens is that the speed changes, and if the light is actually going at an angle to the normal, then that means if the angle of incidence is greater than 0, then you will see the light bending. And this bending of light, because the speed changes, is called refraction. One of the terms used is refractive index. The letter for refractive index is N. It's comparing how much slower light travels in that medium compared to air. So light travels fastest in air or a vacuum, and the speed of light in air or vacuum is 3 times 10 to the power of 8 meters per second. This value should be given to you. it might be useful to remember that if you're comparing the speed of light in a vacuum to the speed of light in air or vacuum, it's going to be the same number. So refractive index of air is 1, refractive index of everything else is greater than 1. So it tells you how many times slower light travels in that medium compared to air. So these are just some examples of how to draw a diagram to show refraction of light. So if there is a coin at the bottom of a pool, so that's your coin, and what happens is you need to draw two rays of light coming from the coin, and it's going to, because it's going from water, which is more dense, to an optically less dense medium, it's going to speed up, so it's going to go away from the normal. But the eye cannot see light bending, so it believes that it's coming from where you produce this. So this is where the coin appears to be, but it's actually there. So this is called the real depth, and that's the apparent depth. And this one just shows that the faster light travels, the more it bends, and your angle of incidence or refraction is always measured from the normal. So that's your incidence, that's your refraction. Okay, and use a ruler, draw straight lines, don't forget the arrows. Okay, then the formula associated with refraction is, so it's n1v1 equals n2v2, where v is the speed, n is the refractive index, and theta 1 and theta 2 are the angles. So n1 sine theta 1 equals n2 sine theta 2. Then moving on to critical angle and total internal reflection. When light travels from a slower, like from water to air, light goes faster in air, so from a slower to a faster medium, the angle of incidence, for which the angle of refraction is 90 degrees, this angle is called the critical angle. Okay, and if you go any bigger than the critical angle, there's not going to be any refraction, but all of the light is going to get reflected within the same medium. So that's called total internal reflection. And you use the same formulas. This is called Snell's law. So use the same formula, n1 instead of theta 1, this is critical angle, equals n2 sine 90. Because sine 90 is 1, it reduces to this. And that's how you find critical angle. Okay. Right, moving on to lenses. So we're only looking at concave and convex lens. A concave lens is actually a diverging lens, and it's got a negative focal point because parallel rays diverge, they go away, and they appear to come from the focal point, whereas a convex lens is a converging lens with a real focal point. Okay, just remember, for a lens, light travels through, it goes on to the other side, but for a mirror, it gets reflected. So just look at your question carefully to see if the ray diagram is for a lens or for a mirror, so that you, and the lens have got on both sides, because it's transparent, you got 2 focal points, and you don't have C, but you got 2F, okay, twice focal length. Okay, that's how you draw ray diagrams for lenses. I've drawn them side by side, just pick 2 of the easiest rays. So what I've done is, for a concave lens, one ray parallel to the principal axis appears to come from the focal point and diverges. Another one goes back and forth. Another one goes through the optic center. So the center of the lens is called the optic center. Where they appear to meet, you get this little image. So it's virtual, upright, diminished. Okay, and same side of the lens is the object. Convex lens, light goes through, but it actually goes through the focal point. The other one through the optic center, and where they actually meet, you get your image over here. So it's real, inverted, enlarged, and it's beyond 2F. The lens formula is exactly the same as the mirror formula. So you've got both these, and you again use real is virtual. Sorry, real is positive, virtual is negative. So I hope that helps.